Welcome. In this video, we are going to derive the Michaelis Menten equation to help us describe the kinetics of enzymes as they react with substrates. We begin with our enzyme, represented by capital E, reacting with the substrate S. The first step is for E and S to join together in what we call the enzyme-substrate complex, also known as the Michaelis complex. This is reaction 1. And notice the double arrows, meaning the reaction can proceed both forward and backwards. The second step in this mechanism is for the enzyme-substrate complex to break apart, giving us the enzyme and the product P. This reaction is only given a single arrow, since we are examining the kinetics very early on, so not enough products P have formed to make the backwards path for reaction 2 noticeable. We are now going to assign variables for the rate constants for these reactions. To make things simple, let's call K1 the forward part of reaction 1, K-1 the backwards reaction, and K2 for the forward reaction for reaction 2. Remember that the backwards reaction for number 2 is not included since it is negligible at this point in the game. To verify that this mechanism is valid, we just need to add reactions 1 and 2 and quickly see that the two ES's and the two enzymes cancel out, leaving us with our net reaction, the substrate, going to product. Let's begin to solve this baby. We make a steady state approximation, meaning that the creation of the enzyme-substrate complex is equal to the sum of all reactions decreasing its concentration. In other words, reaction K1, which creates ES, minus K-1, which consumes ES, minus K2, which also consumes ES, is all equal to 0. We write this as the instantaneous rate of change for ES over dt, which equals the reaction of K1 times concentration E times concentration S, minus K-1 times ES, minus K2 times ES, and all this equals 0. These expressions, such as K1 times E times S, mirror our method for initial rates, where reaction rate only depends on the concentrations of the reactants. For the K1 reaction, the reactants are E and S. This equation of K's, E's, and S's is great and all, but one problem we have is that it is very difficult to determine the value of unbounded enzyme E. To solve this problem, we define E sub T, E total, to represent the total concentration of enzyme. E sub T must then equal the concentration of E, the unbounded enzyme, plus the concentration of ES, the bounded enzyme. We subtract ES from both sides and solve for E. We now substitute E sub T minus ES into our previous equation for E. We then have 0 equals K1 times the quantity of E total minus ES times S, minus K-1 ES minus K2 ES. If we distribute the K1 and S in the first term, we are left with K1 times E total times S, minus K1 times ES times S, minus K-1 times ES, minus K2 times ES. Our goal is to solve for the concentration of ES, so we move all terms with ES to one side of the equation. We then factor out the ES, leaving us with ES times the quantity of K1 times S plus K-1 plus K2 equals K1 times E total times S. We divide to leave ES by itself and arrive at concentration ES equals K1 times E total times S divided by K1 times S plus K negative 1 plus K2. We multiply both the numerator and denominator by 1 over K1, leaving us with ES equals E total times S divided by S plus K negative 1 plus K2 over K1. This solution for concentration ES is fine and dandy, but we still have a little bit more to go. The instantaneous rate of change for the product P is a function of its reactants. In this case, there is only one reactant for reaction K2, that's ES. So we know that the instantaneous rate of change for product P equals K2 times concentration. But wait, don't we have an equation for the concentration of ES? You're right. We substitute our equation in for ES and are left with the Michaelis Menten Equation. Velocity, which is just another way of saying the reaction rate, or dP over dt, equals kcat times E total times S, divided by S plus Km. Don't worry about these new variables, they're easy. Kcat is just another name for K2. The reaction constant, Kcat, or K2 for those of you who don't like change, is called the turnover number. The turnover number is the maximum number of molecules of substrate S that an enzyme can convert to product per catalytic site per unit of time. I know that's a lot. It simply measures how many molecules an enzyme can work with per second. Notice in the numerator, we have Kcat times E total. Let's think about this in words. We have the total concentration of enzyme times the maximum number of molecules an enzyme can catalyze per second. If all the enzyme is reacting with the most molecules possible per second, we have the maximum rate, signified by V velocity max. If that confused you, here's a comparison. Let's say we have a car that goes at its best 30 miles per gallon. This is like our Kcat value. It measures how much bang we can get for our buck. How many miles can we get for a gallon? How much substrate can an enzyme catalyze? If we had 10 gallons of gas, we know that 30 times 10 gives us a maximum range of 300 miles. In the same manner, if we have a certain number of enzymes working, or more formally a certain concentration working, if we then multiply that by the turnover number, the maximum work one can do individually, we then get the maximum amount of work they can all do together, which is the maximum velocity or maximum rate of the reaction. Yet another way to think about this, I know it's a lot, is to look at reaction 2. We know that the rate of production of product, the rate of reaction, equals K2 times concentration ES. As ES goes up, the rate of reaction also increases. So if ES equals E total, meaning that all the enzyme is bounded or saturated with substrate, then the reaction rate or velocity is at its maximum. The bottom line is Kcat, the turnover number, times E total equals Vmax. Now let's look at Km. The Km in the denominator, called the Michaelis Constant, is equal to K negative 1 plus K2 divided by K1. What if the concentration of substrate was equal to Km? We would then have velocity equal Vmax times S divided by S plus S, or 2S. The S's in the numerator and denominator would cancel, leaving us with Vmax over 2. This means that Km is the concentration of substrate S at which the reaction rate is equal to half the maximum velocity. Km also tells us about the affinity of the enzyme for its substrate. If Km is low, meaning a small amount of substrate is needed to reach half the maximum velocity, then the enzyme has a high affinity for its substrate. If Km is high, then a lot of S is needed to reach half of maximum velocity, and the enzyme has a low affinity for its substrate. Well, that's the Michaelis Menten equation. Velocity equals V max times S divided by S plus Km. Thanks for watching.